Yes, hi everyone. Welcome back to Power Systems 2 class, that is online classes, Power Transmission System Design. Yes, so now we are in calculation of inductance for transmission line. Yes, already we derived the expression for inductance of a single phase two wire line. That is, what is the expression we got? Yes, which expression we got from that? That is LA is equal to 10 power minus 7. This is loop inductance. 10 power minus 7 to 1 plus 4 into ln d by r. Yes, this is the expression already we got. For calculation of inductance for single phase two wire line. Yeah, single phase two wire line, because some noise is there due to fan. So let me switch off this. Yes, the next one is, so now I already told you, so let us we have some alternate expression for this. That is yes, as we have the expression as the inductance of the line, single line, LA is equal to, it is not loop inductance, it is single inductance. What is that? 2 into 10 power minus 7, 2 into 10 power minus 7, next 1 by 4 plus 2 into 1 by 4 1 by 4 plus ln d by r, like this. Okay, yeah, this is the expression for the inductance of the solid wire, that is single solid wire. So now what I am doing in the sense, I am inserting this 2 into 10 power minus 7 inside here. Then this equation will be LA is equal to 2 into 10 power minus 7 into 1 by 4 plus 2 into 10 power minus 7 ln d by r. Yeah, so here we can observe that the inductance of the solid wire contains the two terms. First one is 2 into 10 power minus 7 into 1 by 4 is one term, and second term is 2 into 10 power minus 7 ln d by r is another term. That is, the first term is constant. This is constant, and it is depending on the the distance and radius of the solid wire. The distance and radius of the solid wire. So then how you can simplify this in the sense? So here so let us we consider that is LA is equal to 2 into 10 power minus 7, as it is 1 by 4 and here I can write ln E base E or ln E. Yeah, ln E. So what is the value of ln E? The value of ln E is 1, because log E base E. For log E base E, the value is 1. So hence here I am directly writing as 1 by 4 ln E. What is that value? 1 by 4 into 1 only. It is nothing change. No change. Plus ln d by R. Ln d by R. Is it right? So now how I can write in the sense ln E 1 by 4 ln E can be written as, so just I want to remove this term. This will comes here like this. Okay. Ln A plus ln B is equal to ln AB. So then it is 2 into 10 power minus 7 ln d e power 1 by 4 by R. Now still I want to reduce this equation, that is I want to remove e power 1 by 4. So e power 1 by 4 I want to remove. So in the numerator I want to keep d as it is. The denominator R has to be changed. So hence what I do in the sense LA is equal to 2 into 10 power minus 7 ln d by R into e power minus 1 by 4. Yes, can I write like this? Yes, what I have done, just I move e power 1 by 4 in the numerator to the denominator. Then it becomes e power minus 1 by 4. And if you type the value of e power minus 1 by 4 in your calculator, this will come 0.7788 approximately. 0.7788 approximately. So hence here I used to take as R dash, which is equal to R into e power minus 1 by 4, that is equal to 0.7788 into R, like this. Okay. So therefore what is expression for inductance of the solid wire? That is given by LA is equal to 2 into 10 power minus 7 ln d by R dash. Ln d by R dash. So do you got this expression? Yes. Now what is R dash? Where R dash is equal to 0.7788 into R. Okay. Yes, if for loop inductance in the sense 2 into LA, you can calculate. Then it will become 4 into 10 power minus 7, like this. This is the inductance of single phase two wire line and the alternate expression for the inductance of solid wire and loop wire. And here we have written one term. What is that in the sense? R dash. R dash is equal to 0.7788. This is also considered as geometric mean radius. So what is this? Geometric mean radius. Geometric mean radius is R dash is equal to 0.7788 into R. Okay, this is geometric mean radius. Okay, now let us find the inductance of the three-phase overhead line. Three-phase overhead line. So now let me take, this is conductor A and this is conductor B and this is conductor C. Three conductors. These three conductors are current carrying conductors. These three conductors are current carrying conductor. Now let us assume that the distance between these two is D1. The distance between these two is D2. The distance between these three is D3. Okay. And we also assume that the conductors A, B, C are carrying the currents IA, IB and IC respectively. And we assume further as the loads are balanced. When the loads are balanced, we can write IA plus IB plus IC is equal to 0. The loads are balanced, then we can write IA plus IB plus IC is equal to 0. Now there will be the flux linkage with conductor A due to its own current and also due to the mutual inductance effects of IB and IC. Yes, as we discussed earlier. Yes, what is that in the sense? The flux linkage due to conductor A. Due to conductor A, flux linkages with the conductor A due to its own current, which is given by psi 1 is equal to mu naught IA by 2 pi 1 by 4 plus integral r to infinity dx by x. This is the flux linking with conductor A due to the flow of current in the same conductor or due to its own current. Now, due to the B current, IB, yes, what is the expression? Psi 2 is equal to, psi 2 is equal to, yes, what is the equation? Mu naught IB by 2 pi into, yes, what is the distance between A to B? A to B distance is D3. So hence it is D3 to infinity dx by x. And similarly, what is psi 3? Psi 3 in the sense the flux linking with A conductor due to the flow of current in the C conductor. So which is given by psi 3 is equal to mu naught IC by 2 pi integral. What is the distance between A to C? A to C it is D2 to infinity dx by x. Yes, at last final. What is the total flux linking with conductor A? That is psi A is equal to psi 1 plus psi 2 plus psi 3. Psi 1 plus psi 2 plus psi 3. So already we have the expression for psi 1. That is psi 1 is mu naught IA by 2 pi 1 by 4 plus integral r to infinity 1 by x dx. This is psi 1. And what is psi 2? Mu naught into IB by 2 pi into integral d3 to infinity dx by x. Next, what is psi 3? Mu naught IC by 2 pi integral d2 to infinity dx by x. Okay, now you simplify this entire equation. That is, you do the integration and you can common the terms like this. That is, if you common mu naught by 2 pi first, psi A is equal to mu naught by 2 pi. If you common this, then IA into plus IA into 1 by 4 plus integral r to infinity dx by x. This is the coefficient of IA. And what is the coefficient of IB? Plus IB into integral d3 to infinity dx by x. Then what is the coefficient of IC? Plus IC into integral d2 to infinity dx by x. This is psi A when we common mu naught by 2 pi. And still I want to represent, I want to expand this. So how it is in the sense, first I want to do the integration. Yes, dx by x, integral dx by dx corresponds to ln x. So ln x in the sense ln infinity minus ln r if you substitute the limits. So if I write like this and if I substitute all these values, and this will becomes as psi A is equal to mu naught by 2 pi. The first one is IA into 1 by 4 minus ln r. 1 by 4 minus ln r. Okay, this is the coefficient of IA, and IB coefficient is minus IB into ln d3. Yes, we will write infinite terms later. Okay, minus IC into ln d2 plus ln infinity into IA plus IB plus IC. Has to do with some patience. So otherwise you may not get this answer. And we know that as the loads are balanced, we should know IA plus IB plus IC is equal to 0. Therefore this term will be 0. Hence what is the remaining thing? Psi A is equal to mu naught by 2 pi into 1 by 4 minus ln r into IA minus IB into ln d3 minus IC into ln d2. Ln d2. Suppose for example there is some symmetrical spacing is there. Symmetrical spacing in the sense, if three conductors A, B and C are placed symmetrically at corners of the equilateral triangle of side small d. So therefore what we can say, so here for symmetrical spacing, it is very clear that symmetrical spacing. So for symmetrical spacing, so here we can write d1 is equal to d2 is equal to d3 is equal to d. Okay, so then how you can write the equation? Psi A is equal to is mu naught by 2 pi 1 by 4 ln minus ln r to IA minus IB plus IC into ln d, because we assume that d1 is equal, d2 is equal, d3 that is equal to small d like this. Now we know that IB plus IC plus IA is equal to 0. So hence IB plus IC is equal to, what is this value? This value is minus IA. And if you substitute that, then this will becomes the plus IA into ln D. So hence if I want to find out the value of psi A, that is psi A is equal to psi A is equal to mu naught IA by 2 pi into 1 by 4 plus ln D by R. This is the finalized value. So inductance of the single conductor in three phase. So which is given by flux linkage, which is given by mu naught IA divided by 2 pi into 1 by 4 plus ln D by R. So now still we can reduce this. Yes, how we can reduce? Inductance is equal to, this is flux linkage, inductance is LA is equal to psi A by IA, then this divided by IA for LA. So hence IA get cancelled. Then what is the remaining thing? Mu naught by 2 pi 1 by 4 plus ln D by R. 1 by 4 plus ln D by R. And here if I substitute the value of mu naught, that is mu naught is equal to 4 pi into 10 power minus 7. Substitute the value of mu naught. Then the expression for LA is given by LA is equal to 10 power minus 7 1 by 2 plus 2 ln D by R. 2 ln D by R. Suppose this is the expression for inductance of A line. Similarly, we can derive for B and C also. Suppose for unsymmetrical spacing, unsymmetrical spacing, unsymmetrical spacing in the sense when three phase line conductors are not equidistant from each other, the conductor spacing is said to be unsymmetrical. Under such conditions, the flux linkages and inductance of each phase are not same. A different inductance in each phase results in unequal voltage drops in three phases, even if the currents in the three conductors are balanced. Due to the unequal inductance, the voltage drop in three phases will be unequal. Therefore, the voltage at the receiving end will not be same for all phases. In order that voltage drops are equal in all conductors, we generally interchange the positions of the conductor at regular intervals along the line, so that each conductor occupies original position at every other conductor over an equal distance. Such an exchange of position is known as transposition. So therefore what we do here, so when unsymmetrical spacing is there between the three conductors, this is conductor A, B, C, the distance are not same. When the distance are not same, then what we say? The inductance of each phase is also not same. When the inductance of each phase is also not same, so then the voltage drops are unequal. Even though the current is balanced, but voltage drops are unequal. In order to avoid that, what we do in the sense, you do the transposition. Yes, we do transposition in the sense, so regularly, so we need to change the positions of the three conductors Regularly we need to change the position of 3 conductors. Yes. So just to keep this topic in mind, that is the transposition. So I will discuss about this transposition next class. So now let us we see one or two problems. Yeah, the problem is like this. Yes, what is problem in the sense? Just write down the problem. Yeah, write down the problem. All of you take your notebook, write down the problem. A single phase line, a single phase line has two parallel conductors, has two parallel conductors 2 meters apart, 2 meters apart. The diameter of each conductor is, the diameter of each conductor is 1.2 centimeters. Then calculate loop inductance per kilometer of the line. Calculate loop inductance per kilometer of the line. So first here we know that the two conductors are there, as it is the single phase line. The two conductors, parallel conductors, the distance between these two is 2 meters apart. 2 meters apart, and the diameter he has given. So therefore radius is diameter by 2, 1.2 by 2, this is 0.6 centimeters. 0.6 centimeters. So here either we can convert centimeters to the meters, or we can convert meters to centimeters. So whatever it may be. So here I want to convert the centimeters to meter. That is 0.6 into 10 power minus 2 meters. Now what is the inductance of the single phase line? Yeah, what is that? That is loop inductance. Loop inductance already we have the formula, that is L is equal to 10 power minus 7 1 plus 4 ln d by r. 1 plus 4 ln d by r. So this is inductance per loop inductance per meter length. Loop inductance per meter length. So then if you substitute this, you may get 24.23 into 10 power minus 7 henries. 10 power minus 7 henries. Then what is loop inductance per kilometer? This is loop inductance per meter. Loop inductance per kilometer, in the sense you need to multiply this with 1000. So therefore L is equal to 24.23 into 10 power minus 4 Henry, that is Henry, or you can also write 2.423 millihenries. 2.423 millihenries. Okay, I hope you got this. Yes, let us stop here. So we will see the remaining concept, that is transposition and other problems, that is problems of three phase line, and the conclusion of all inductance. Well, hopefully, so next with the next two classes we'll finish this inductance, then we'll start the capacitance. And do prepare well for the notes. So notes are also very important. Just you take the running notes. Okay, and after completion of your class, if you have any doubts, you can also go to the YouTube. So in the YouTube also I am uploading this one. Yes, thank you for watching this. Stay home, stay safe.